All right, so today we're going to talk about multiplying matrices together. Again, the product of two matrices, A and B, is defined by provided the number of columns in A is equal to the number of rows in B. So again, yesterday we spent some time labeling what type of matrix you have, the row by the columns. And so when we are multiplying, in order to multiply matrices together, the number of columns in the first matrix has to match the number of rows in the second matrix. We're going to learn about some of the properties about associative and commutative here in a little bit, but when they have your matrix set up in a certain order, as I look at my number of rows, so rows, columns, so my columns, and then my rows for this one, they have to be the same number. If they are not the same number, then I cannot multiply the two together. My final answer ends up being the outer dimensions is what creates my answer matrix. So this one is a lengthy process, and so I will take you through it as slow as I can. Try to write down as much as you can with it. So as I look at, again, the definition, they just say the ith and the jth column. That's just generic terminology that's inside the book. So what we do more or less is we're going to take the top row and I'm going to multiply it by the first column. And that is going to give me what the answer for the very top left cell is. So I would actually do A times E and add to it what B times G is. And once I get done with multiplying A and E, B and G together, I would add those two answers together, and that gives me the answer in that top left cell of the matrix. Once we get done with that, we're going to take the same A and B, that top row, and multiply it by F and H, and that gives me what's in the top right-hand part. So A times F plus B times H, and that gives me the number answer that's in the top right. Now we're going to repeat the same process with the bottom row. We take the bottom rows C and D, multiply it by E and G. We would do C times E, add to it what D times G is. So that's the answer for that bottom left. And then the final part, we take the bottom row times the far column, and we would say, all right, that's going to be C times F plus C times H, and that gives me the answer in that cell. And again, what those simplify down to, it gives me my 2 by 2 matrix. Again, I'm allowed to do this because the inside part, the number of columns is 2 and the number of rows is 2. And so that allows me to make that I can do my multiplication. Yes? Why is it not C? It should be D times H. Thanks, dear. Should be D times H. Thank you. All right, so let's see if we're careful here. So as we do an example, and I'm going to do it the long way. I'm not going to do the math in my head. We're going to go 3 times 2 times the negative 1 times 6. So that's going to be 3 times negative 1. Add to it 2 times 6. That's the top left cell. Then I'm going to go ahead and do the same thing with the 3 and the 2 with the 4 and the 5. So 3 and 2 times 4 and 5. So that would be 3 times 4 plus 2 times 5. Again, I'm trying to space this out so I don't jumble stuff up together. I should have 4 distinct answers here since I'm doing a 2 by 2 times another 2 by 2. On the bottom, we're going to take the negative 1, the negative 7 and 8 and multiply to the first column. So we would have negative 7 times negative 1. Add to it what 8 times 6 is. And then as we erase all that mumbo jumbo, we take the negative 7 and 8 times the 4 and the 5. So it would be negative 7 times 4 plus 8 times 5. And again, as you look at it by showing this stage, and I know a lot of us don't like to show the stage, but we should see a pattern here. We should see patterns with numbers being used twice in certain locations. We should see the first matrix numbers being used twice in the top row and twice in the bottom row. We should see the numbers in the second matrix being used twice in both of those rows as well. So you got to be careful. It's really complicated when we get bigger matrices. We're just doing a 2 by 2. We start doing a 3 by 4 times a 4 by 3. The math gets even bigger. So now we're going to go through and we're going to simplify this. Let's see. 3 times -1 is -3 plus 12. That would give me 9 for the top left. Then let's see. 3 times 4 is 12 plus 10 gives me 22 for the top right of the answer matrix. And the bottom left, we would have 7 plus 48, which is 55 for the bottom left. And then we'd have -28 plus 40, which should be 12. Hopefully some of you are working ahead of me, got the same numbers. If I made a boo-boo, please let me know. I think I did pretty good on that one. Okay. So there's my answer matrix. Again, I would not advise doing this stuff in your head. It's a lot to keep track of. It's okay to show your steps. And we got to remember, sometimes on the end of course exam, we just have to have the right setup. We don't have to even execute it all the way out. It's like, which one shows the right display of multiplying this times this and plus this times this. So we don't always have to multiply it out. So that's why we want to show the steps in it, because it kind of, we get asked those questions from time to time. All right, next one here. We have again, rows by columns. We have a 1 by 2 times a 2 by 1. So since the inner parts match, that means we can go ahead and do the multiplication here. We didn't check it on the last one, but we got to make sure we check it from here on out, because if those inner numbers don't match, then we can't do it. So as I do this one, we take this row, multiply it by that column. So that gives me 5 times 4 plus -2 times 9. There's no more rows and columns, so I'm just going to simplify that. So with that in mind, we would have, 20 plus a -18. So my answer is just 2, and it's inside the box. Now, that answer looks a little weird. Yes, we need the closed brackets on it to indicate that it's a matrix. So if you just type it in as a 2, it's going to mark it wrong. You got to put it in a matrix box, that little generic one-cell box that's on the thing. And what we got to remember is my answer matrix is basically taking the last numbers of the outside numbers of our dimensions, and we're saying, okay, we got a 1 by 1 matrix answer. Well, yeah, we got one row and one column. That's all we got. We got one thing. There's one row, one column. This is technically a 1 by 1. One row by one column. Even though it doesn't look anything different than just one thing down there, that's technically a 1 by 1 matrix. So it is possible for the matrix to change all the way down to where it's a single number. All right, next one here, we have, let's talk about our dimensions. We have a 3 by 2 times rows by column, a 2 by 3. Am I allowed to multiply those together? Yes, because again, the inside numbers match. Now my answer should be a 3 by 3 matrix, because that's the numbers on the outside. So when I get done with this one, I'm going to have a really big matrix. Okay, so I'm going to go ahead and set it up and have a really big matrix there. And again, we'll take our time. Top row gets multiplied to the first column. So that would be 3 times a -1 plus -4 times -6. That's the top left. Remember, 3 by 3 means that if there's 9 cells. Okay, a 3 by 3 means that there are 9 cells. There's 9 cells on the inside. So I'm going to erase my column because I'm writing really big. I'm going to write the far side there and make it a little bit wider there. All right, then the middle. Now on the middle top row, we would take our 3 times -4, multiply it by the second column. So that would be 3 times 7 plus -4 times 2. And then when the last one, we would do 3 times -2 plus -4 times 4. I didn't even still squeak it in there. I didn't go out far enough. -4 times 4. All right, so there is my top row. Now I got to follow suit with the rest of these. All right, so now I take the middle row and do the same thing. 6 times -1 plus 5 times -6. Then it would be 6 times 7 plus 5 times 2. Then it would be 6 times -2 plus 5 times 4. And to me, if you keep the order similar, you should be able to compare up above things that should be repeated. The number before the parentheses should be repeated in some, or in the parentheses should be repeated as you go down, is what should happen. From one row to the next row. Now, as I do the last row, we're going to take that 1, 0 and multiply it in. So that would be, let's get back to our structure here. 1, come on, pen. 1 times -1 plus 0 times -6. And then we have 1 times 7 plus 0 times 2. And then we have 1 times -2 plus 0 times 4. So there's my structure. Now it's time to just simplify and do the math. All right, let's see. That's -3 plus 24. I'm going to write my answer down below it. That'll be 21. Then we have 21 minus 8. That would be 13. -6 plus a -16 is a -22. So that completes my top row. Then we say -6 minus 30 would be a -36 for the second row first term. Then we have 42 plus 10, which would be 52. -12 plus 20, which would be 8 for the finish up the second row. And then the last one would be -1 plus 0, so that's -1. 7 plus 0, which is 7. -2 plus 0, which is -2. And then there's my answer matrix. Again, not a short process. Easy to lose track of things. I would keep it in a nice format to where you can notice, hey, the stuff at the end here in my parentheses match on each of the rows. That way I don't forget something. So I keep a nice little structure here. I'm going to talk about that, how I had to do that for one of my papers for my master's and stuff. So, it's easy to lose track of something. Does anybody need my orange writing any longer as I get ready to scroll up? We're okay? I was assuming I was going slow enough because that's not a fast topic. All right, so the identity matrix, the next little notes thing here. When we have a matrix, whether it's and again, an identity matrix basically has to have the same number of rows and columns. So an identity matrix is either going to be a 2x2, a 3x3, a 4x4, a 5x5. It is going to have the same number of rows and columns for one to be classified as an identity matrix. And it is called the identity matrix when it consists of ones on the main diagonal. That means going down from top left to bottom right. And all the other elements are zeros. When I multiply, and this is the last statement there, it says if matrix A is an identity matrix, when I multiply a matrix by the identity matrix, I get basically what I started with. So when you multiply by the identity matrix, you just get back to the original thing. So it's almost like, if I take the number 3 and multiply it by 1, what's my answer? My answer is 3. So that's what the matrix, the identity matrix is saying is, if I take some matrix that is like 2, 3, 4, and 6, let's call it a 2x2 matrix there, and I multiply it by the identity matrix, then my answer matrix is still going to be 2, 3, 4, and 6 in those same spots. Multiplying by the identity matrix doesn't change the cells. It keeps it the way it is. Now, we can show that it's that way by actually going through and doing what we just did in the previous part. All right? But we don't have to. Multiplying any matrix by its identity matrix results in the original matrix. It doesn't change. It doesn't transform. Okay? So that's the little definition there. Some properties with matrix multiplication, because not all properties with normal math that we learned with associative and commutative actually work in the matrix world. So they're saying here, let A, B, and C be some type of matrices. Let I be the identity matrix, and let K be some type of scalar multiple. The associative property of matrix multiplication works, which means that if I have A times the quantity B times C, I would get the same answer as if I did matrix A times matrix B first, and then multiplied that by matrix C. So that one's saying it doesn't matter the grouping of my matrices and multiplication, I would still get the same answer even if I change the grouping of the two things that I multiply together. All right, and sometimes it may be better to do it that way because it may be working with smaller numbers to go through stages. We have what's known as the left distributive property and the right distributive property. So if I have a matrix in front of a sum of matrix, I can actually multiply that in. And that would be the same thing as just adding the two matrices together and multiplying by the matrix out front. The right distributive is saying if I have a sum of matrices in the beginning times a matrix at the back, I could actually multiply the matrix at the back times each of the individual matrices and then add the answers together, is what that one's saying. The associative property of scalar multiplication says that if I have two matrices being multiplied together times a scalar multiple, I can multiply the scalar multiple to either one of the matrices, just one of them, not both, one of them, and then multiply it by the other matrix. And it doesn't matter the order of who I multiply to. That's why they say that, hey, K times A times B is the same thing as A times K times B. The key thing is you can only multiply the K to one of the matrices. So if you need to make a little note there, you can only multiply scalar. So I guess scalar is supposed to have a C there, isn't it? I like making up my own words. Scalar to one of the matrices. And then the last one, the multiplicative identity property, just again says that if I take some matrix, multiply it by the identity matrix, I get back to my original matrix. And again, it doesn't matter the order that I multiply it. Whether it's the matrix times the identity or the identity times the matrix, I still get the original matrix, is what I get. So we got some practice problems where we get to find the product of these things here. Remember, if certain things don't match, then I got to say can't multiply. So when I write the dimensions, the first one is a 1 by 2 times a 2 by 1. Am I allowed to multiply those two things together? Yes. All right, so let's go ahead and find that answer. So that would be 6 times 3 plus negative 1 times 2, which is 18 minus 2, which gives me a whopping 16. Number 2, we have a 2 by 2 times a 2 by 2, so I'm able to multiply those two together. So take your time. We got the 6 and 1. 6 times 2 plus 1 times 0. Then we have the 6 and 1 times the last column, so 6 times negative 5 plus 1 times 4. Oops, that's a 14. Then we go bottom row, negative 4 times 2 plus 3 times 0. And then negative 4 times negative 5 plus 3 times 4. So I have my cells set up. Again, I should see some repeats in certain locations. And then now we just simplify. That'd be 12. And on the next one, that'd be negative 30 plus 4, which would be negative 26. And that would be negative 8 plus 0, so negative 8. And then 20 plus 12, which is 32. All right, next one. We have a 2 by 2 times a 3 by 2. Am I allowed to multiply? Very good. We can't multiply. So we move on to the next one. We have a 3 by 2 times a 2 by 3. Can I multiply? Yes, we can multiply. This is going to be a long one, because our answer is a 9 by 9, or a 3 by 3, sorry. Our answer is a 3 by 3, so it's got 9 cells in it. So, whew. You want to race? All right, 1 times 4 plus 6 times negative 5. 1 times 0. Whoopsies. Put that back there. 1 times 0 plus 6 times negative 1. 1 times 8 plus 6 times 3. Next row is 2 times 4 plus, sorry, it's a negative 2 times 4 plus negative 3 times negative 5. Negative 2 times 0 plus negative 3 times negative 1. Negative 2 times 8 plus negative 3 times 3. And then the last row would be 7 times 4 plus 2 times negative 5. 7 times 0 plus 2 times negative 1, and then 7 times 8 plus 2 times 3. All right, let's clean that up a little bit. Let's see, that's 4 minus 30, so negative 26, negative 6 in the middle, 8 plus 18, which is 26, negative 8 plus 15, which is 7, 0 plus 3, which is 3 in the dead center, negative 16, minus 9 is a negative 25, 28 minus 10, which is 18, negative 2 in the middle, and then 56 plus 6, which would be 62. Now again, it's okay if it takes a little bit. I mean, I didn't give you a ton of problems for homework. I understand that it takes a little while to do the math in each of the cells. Okay.
How many problems do we have?
Oh, I think somewhere no more than 20. I don't think I gave you too many. I used this assignment back in the fall, and I didn't give that many. Just because it's a tedious, multiplying takes a while and stuff. And so I cut down on the number of problems to make it go a little bit quicker and stuff on there. The other thing we got to keep in mind is right now we're doing everything by hand. That way we can spot all the original setups. Eventually I get to teach you how to use the TI calculator to do a lot of this stuff for us, okay? Which will speed it up. But again, we got to know the fundamentals. We got to know the fundamentals of how does it come about as we do things. We have one more problem, and I always sneak in word problems because that's real life. Now, I understand that in real life, you guys aren't going to break out your calculator and a matrices thing and create a matrix to do things, but we could. We could do that if we wanted to solve our things. And so I want to show you how we can take a word problem and put it into the matrix format, and then we could create, we can find the answer for what we're looking for. That leads us into tomorrow's topic where we're basically, in a way, solving systems of equations today is what we're doing. To me, as I look at it, we have this menu thing where Class A, 10 meals are chicken, 12 are beef, 8 are vegetarian. Class B, we got 11 chicken, 14 beef, 7 vegetarian. Then they come over here and they tell us that, hey, we have some type of cost thing. We got some type of cost matrix coming over here. So just want to show you how we can turn this into a matrix from a word problem. So as we do this, what I'm going to do is I'm going to first write down a little key here. I have Class A, and then I have Class B. And I'm going to let this first matrix be the meals. I'm going to let that be the meals. And when we go back to the menu, we can go back to the menu and look at it saying, okay, we got chicken, we got beef, and we got veggies. So for my column headers, I'm going to say chicken, beef, and veggies are my little column headers. And then now I'm going to put the numbers for each of the classes that are associated for each of those menu items. So Class A said that it had 10 chicken, 12 beef, and 8 veggie meals. Class B had 11 chicken meals, 14 beef meals, and 7 vegetarian meals. Now, back in 8th grade and 9th grade, we would have said, okay, let X, Y, and Z, each of them stand for one of those items, and we would have said like 10X plus 12Y plus 8Z equals some total amount. And then we would have done the same thing with the Class B. We would have actually created some type of mathematical equation with X, Y's, and in this case, Z, because we got three things. 8th grade, 9th grade, it was just 2 items, X and Y's. Now we got 3 things. So there's my first matrix. Now, what we want to go through and figure out, they give us in the word problem, they said each student in 2 classes submit meal choices. Each chicken meal costs 6, each beef costs 8, each vegetarian meal costs 4. Use the matrix multiplication to find the total cost for each of the classes. So I'm going to multiply that matrix by a cost matrix, and the answer will be a total cost for each one. We'll get a total cost matrix. So they tell us that chicken is 6, and now here's the key thing. When I set my cost matrix up, I got to go the same order I did on top. I got to go down vertically. Chicken, beef, veggie. And we know that the chicken is $6, beef is $8, and a veggie is $4. Now, the C, B, and V in my diagram are just there for indicators so that when I multiply for my total cost matrix, when I multiply the Class A's individual orders to that cost matrix, and again, those aren't negatives, those are just bullet points there. We would say, okay, what is 10 times 6 plus 12 times 8 plus 8 times 4? And that's going to tell me what the total cost for the meals for that class is. Then I'm going to do the same thing with Class B. I'm going to take 11 people wanted chicken, so 11 times $6. Plus 14 people wanted beef, so 14 times 8. Plus 7 veggie meals at $4 a piece. And then now my final answer, we would go through and just do the math. So let's see, that's 60 plus 96. So 60, 96, and 32. So that'd be 156 plus 32. Is that 189? Did I do that right in my head? 156 plus 32, is that 189? Somebody want a calculator? Double check me. $189, thank you so much. On the bottom one, we would do 11 times 6 is 66. 14 times 8 is 112. And then 7 times 4 is 28. We get to add those 2 together, or 3 together. So that'd be 178 plus 28. That'd be 198. Is that 206? Did I do that right? 66, 112, and 28. Is that 206? Sweet. Awesome. So at Class A's total cost for those meals is $189. And then Class B's total menu, cost is going to be $206 is what it works out to be. So again, we in a way just solved, for a total cost, kind of creating matrices to do our math for it. We get to deal with more systems of equations tomorrow is what we get to deal with. There's no such thing as dividing matrices. We don't have to worry about that. You can only do adding, subtracting, and multiplying. You can do the scalar multiples. And again, we got to remember that certain order things can't be done. Okay? Multiplication in this case is not commutative. I can't change my order of what I multiply when I'm multiplying matrices for the most part, because if I change the order and my rows and columns don't match up when I switch them around, then I may not be able to multiply. The only time multiplication would be okay is if you're doing like 2 by 2 times a 2 by 2 or a 3 by 3 times a 3 by 3. Because no matter which order I put them, I'm going to still have the 3 by 3s and the 2 by 2s. So that's just some things to keep in mind. Let's make sure we got everything there. Perfect.